Perfect. All right. Welcome to, let's make sure this is on. Limiting reactants and percent yield lecture by me. Actually, and leftovers. Perfect. Okay, let's go ahead and get started. So just definitions right off the bat. A limiting reactant, we'll do examples with these in a second. A limiting reactant is limits the amount of product that can be made. So it is completely used up by the reaction. So this right here is going to determine how much product will be made, like how much is possible. Versus this right here is the excess. This is when you're going to have so much that like it, this is when you're going to have an excess or an extra amount of a reactant or reagent. So if you had more of your limiting, you can make more product because you have your extra. So your excess does not limit, right? Does not limit how much product can be made. The excess reactant is not completely consumed because it's obviously in excess. So just remember the difference. Limiting reactant is completely used up by the reaction, and then the excess is not completely. So normally they'll give you two reagents, and they'll ask you to find how much can be made with them. So right off the bat, you want to find the limiting, right? Because your excess is going to give you a skewed answer, like you can't have more than your limiting. So for example, we've got 1, 2, 3, 4, 5 hot dogs, and then we have 4 buns, okay? So how many can we make if this is our formula? If our formula is 1 + 1, right? So we have 1, 2, 3, 4. Perfect. And look what we have left over. We have 1 excess reagent left over, 1 hot dog left over. So our excess is this, which means our bun is limiting how much hot dog in a buns we can have, right? So this is our limiting reactant, and our hot dog is our leftover, it's our excess, okay? So how to find it? If given reactants in grams, we're going to determine how many moles of each reactant are present by dividing molar mass, okay? So we want to find that. We want to find moles with the reagents. And then we're going to want to use mole ratio to determine how many moles of product you can get out of that amount of reactant, okay? Out of both. And then the lesser amount is going to be the limiting reactant, okay? And then if needed, if the problem asks, it most likely will. How much of that limiting reactant, how much can you produce with the 2 reactants? Well, you take your limiting and you convert it into grams or kilograms, whatever. You multiply by the molar mass to get your mass, okay? So let's do a little example here. So X red balls and Y blue balls. Identify the limiting reactant and write a balanced chemical equation describing the reaction taking place in each pair of images. Awesome. So let's see. So let's count them up. We have 1, 2, 3, 4, 5 X's. Okay, and then we have 1, 2, 3, 4, 5, 6, 7, 8 Y's. Well, what's gonna go with what? Well, let's look at this picture right here. So 2 blues for every 1 red. So there's 1, there's 1, there's 1, there's 1, and what is that? Excess. So with our formula, we have 1, 2, 3, 4 reds, so 4 X's, and those are together with 2 Y's, okay? And then our excess is going to be the red, the X, okay? So that is our excess, red is excess, so what is the limiting? Identify the limiting reactant, that's going to be the Y, the blue. Perfect. Does that look right? Yes. Now, let's do a little practice problem here. This reaction makes potassium superoxide useful in self-contained breathing apparatus. How much O2, how much O2 can be produced from 2.57 grams of KO2 and 4.58 grams of CO2. So our mole ratio is going to center around that, okay? So let's try both out. So we need to see which one is the limiting reactant. So 2.57 of KO2, and then we have 4.58 grams of CO2. Awesome. So 1 mole of KO2. Well, what is our molar mass of KO2? I believe it's 71.10 grams of KO2. Now we need to do our mole ratio. So how many KO2s do we have? We have 4. And what do we want? Okay, what is it asking the question? It wants O2. So there are 3 moles of O2. And this we will multiply out to give us... Well, we'll just stop here because we don't need to go any further, just to find the limiting reactant. And then 1 mole of CO2. Well, so let's see what's the molar mass of CO2? 32 plus 12 points, that's be 44.011. Okay, how many moles of CO2? There's 2. And then I got 3 moles of O2. Okay. And if we solve these out, this is 0.0271 moles of O2. And then for the next one, we have 0.1561 moles of CO2. I'm sorry, this is, I'm sorry, hold up. This is also O2. Moles of O2. Okay, so what is less? This one. This is our limiting. So let's change this into grams. And this should give us our answer, which should be 0.868 grams of O2, right? Awesome. Okay, more practice. Baking soda NHCO3 is produced on an industrial scale by the Solvay process. The key reaction is the process is this. Suppose a reaction vessel initially contains 58.5 kilograms salt, and then 18.8 kilograms of NH3, and excess CO2 and H2O. How many grams of NHCO3 is produced in kilograms? Okay, so our mole fraction is going to center around this. We have the salt, and we have NH3. So those are what we're going to find, how we're going to find a limiting reactant. We got to determine which one of those is. And excess, so we don't really care about those much because there's plenty. Awesome, so let's start out with, it's in kilograms, so let's just throw it into grams real quick. 58500 grams of, what are we looking at? NaCl. Perfect. Okay. And 1 mole of NaCl is how many grams? 58.44. Wait. Yes, okay. And then we will do our mole fraction, 1 mole of NaCl. Well, everything here is 1, so there's no coefficients. So we know that it will be, what are we looking for? NaH. We know our mole fraction won't really matter here. Okay. And this is going to give us that many moles of NaHCO3. Perfect. Now we are going to do our NH3 to determine if that will have more or less moles. Cool. NH3 is 17.03. Cool. And then again, it's just 1 mole of NH3 and 1 mole of that NaHCO3. And that's going to give us this. So right off the bat, we know that the NaCl will be our limiting reactant. So we need to change this into grams. Let's see, NaCl, let's see the periodic table. Perfect. So that's, oh, that's right, 84 grams. 1 mole. Awesome. I swapped those. My bad. Perfect. And 84,085 grams, which is going to be 84 kilograms of that. And that is our answer. Perfect. All right, so now we have leftovers. Leftovers deals more with the, with both, obviously, but it involves the excess reactant. So first, determine the limiting reactant, and then we want to calculate how much was used of both the limiting and the excess. And then we will use the limiting reactant amount to calculate how much of the other reactant was used, okay? And then we subtract the amount to use of the excess reactant from the original amount of the excess reactant. Okay, let's do a little problem. Or right here, this little example, we have, remember we have 5 hot dogs, and we had 4 that were used, okay? And so you subtract it, you get 1. That's basically all it is. Let's do a little example here. So how much magnesium nitride can you make if you have 4 grams of Mg and 12 grams of nitrogen? And what will be left over? So first, let us determine what is the limiting reactant. So we have 4 grams of Mg. The molar mass of Mg is 24.305. 1 mole of Mg. And then our mole fraction, there is 3 moles of Mg. And what do we want? We want magnesium nitride. Okay, that's just 1. Okay, so 4 divided by 24.305 times 1/3. 0.05486 moles. Okay, and now we will do this one, 12 grams and 2, to see if this one might be the limiting reactant. 28 grams of N2, 1 mole of N2, and then how many moles of N2? We just have 1, and then we just have 1 mole of magnesium nitride. So now all we have to do is, there we go, 2857 moles of N2. Awesome. That is it. So we know this one is the limiting reactant. Perfect. And now we want to use this. This doesn't matter anymore, right? Because we know that's excess. This is what's actually going to make the amount of reaction. Because this is all we have. It's what's limiting us. So we're going to take this moles and put this into our mole fraction to find out how much of our excess will be left over. So how many moles of, there's 1 mole of Mg, 3 and 2, and how there's only 1 mole of nitrogen. And this is also the answer for the first part of the question, when it's asking how much magnesium nitride can you make. Awesome. And so we convert this, and this is going to be 0.5486 moles of nitrogen. So, oops, my bad. So we want to subtract this from 12 grams, but this is in moles. So we need to put that, take that out of moles. 1 mole of N2 is going to be 28, I believe. Yes, 28 times 28. And that's going to give us, in grams, 1.54 grams of N2. That's how much what was used, right, in the reaction. So now we want to subtract 12, or 1.54 from 12. And this should give us our answer. This is how much excess we have. 46 grams of N2. Perfect. That is the correct answer. Awesome. Now our last concept here is percent yield. So percent yield is going to be, still a definition here, is the actual yield, how much that was actually made, and they'll usually tell you that in the problem, versus the maximum amount of possible yield, which is what we usually calculate in the problems that we do, right? Because in real life you have variables that affect percent yield, maybe something that was left in the pot, temperature. There's a lot of factors that change what the actual yield is. And then we will times that by 100%, and that will give us our percent yield, okay? So here's a little concept question. Our gold extraction should have produced 105 grams of Fe. So should have, what does that mean? That means when we do our calculations, it should have done that. So this is going to be our theoretical. Shoot, how do you spell? I don't think oh yeah, theoretical. Okay. But instead, what they actually got after mining and maybe losing some pieces, 81.1 grams of iron. And that's going to be what we actually got, right? So we're going to throw that into our equation, which is actual over theoretical, right? Usually the smaller one over the bigger one, always, and times that by 100%. So divide them, you're going to get 0.772, times by 100, you're going to get 77.2. And that right there will be our percent yield. Awesome. So here is a practice. An industrial process for producing hydrogen gas is based on the reaction between steam and carbon heated to incandescence, producing a mixture of CO and H2 called synthesis gas or syngas. So we got two problems. Write a balanced equation, chemical equation describing the production of syngas. And then the next question, it's a reaction vessel that initially contains 66 kilograms of incandescent carbon and excess steam produces 6.8 kilograms of H2. What is the percent yield? Cool. So let's start with the first one. Let's write a chemical equation. Between steam and carbon, well, what is steam? It's water. It's a gas. And carbon, oops, that should not have parentheses, plus carbon, okay. I'm not sure if it's solid or gas, but that's going to make a mixture of CO plus H2, okay. Now let's make sure everything is balanced. We have two hydrogens, one carbon, one oxygen. Cool. Awesome, so there's our chemical equation. So if a reaction vessel that initially contains 66 kilograms of incandescent carbon and excess steam, so this is what we have, this doesn't really matter because we have so much of it, produces 6.8 kilograms of H2. What is the percent yield? Awesome. So it's telling us what it produces. Okay, so that's actually what it's producing. It's not saying anything theoretical here. So you could insert an adjective here and say actually produces, right? So remember our equation is going to be actual over theoretical. Actual yield per theoretical. So they've given us actual yield, and we want theoretical yield. So how do you determine theoretical yield? Well, you just do the calculations. So we have 66 kilograms of carbon, and we want to determine how much H2, hydrogen gas, should have been made from this. Okay? So let's convert this into grams. Okay. And then how many grams What is the molar mass of carbon? Well, it's 55.999 grams of carbon for 1 mole. That is not correct. It's 12.011 grams of carbon for every mole of carbon. Okay, and now let's do our molar fraction to get it into H2. Well, we have 1 mole of carbon. We don't have any coefficients here. That's all ones. And we have 1 mole of H2. Okay. Awesome. Well, let's keep going because we're not trying to find the limiting reactant right here, right? They only gave us 1 reagent. All we're trying to do here is find how much should have actually been made. So, let's put this, now we have in our moles of H2, we want to get it to grams of H2. And for every mole of H2, how many grams are there? Well, 2.016 grams of H2. Cool. And, well, that's in kilograms, so we better put it back into kilograms. There are 1,000 grams H2 for every 1 kilogram H2. Now this should give us our correct answer. Let's see. Yep. Yes. Cool. So do some calculations. Awesome. It looks like it's giving us 11.08 kilograms of H2. Awesome. So these calculations right here are telling us how many what should have been made, correct? Let's see here. So now we just put it into our equation. So our actual, So our actual was, they told us in the problem, produces 6.8 kilograms of H2. Well, our theoretical, what we should have actually gotten is right here, what we calculated, 11.08 kilograms of H2. If we do that, looks like it's giving us 0.617. But that is not percentage. Oops. That wasn't good. Hold on a second. Okay, my bad. Okay, this looks ugly. Yay! Okay, I don't know what to do. 11.08 kilograms of H2. That gave us 0.617. And all we have to do is put that into times by 100. And this should give us our answer of 61.7%. Now that should be our theoretical yield. Awesome, where is the answer? Cool. And those are our calculations. Yep. Looks right, about 61%. Awesome. So that is the that is limiting reactants and percent yield as well as leftovers. So that is